This is a tribute to Eddie Van Halen. I'm made the decision. I made a double decision actually. Decision number one is I gotta play my way through the Van Halen catalog now, just as a tribute to maybe the greatest rock and roll guitarist in history. Maybe. Yeah, and by the way, yeah, not arguing who's up there. Hendrix, absolutely. But Eddie Van Halen, I don't know, man. That guy. Anyway, rest in peace, Eddie Van Halen. Getting to the point where these musicians, Eddie Van Halen, Neil Peart earlier this year, these guys were not that much older than me. So, you know, and then it's kind of like, I don't know, you know what I mean? You got these guys my age-ish, and they're dying of cancer and crap. So, anyway, hey everybody. So I've got the video in the chat on Discord. For those of you watching this on YouTube, the video, the address of what you're watching is in Discord, and I also posted the address already because I'm on my game on Canvas, so it's already in the schedule. Cool. Are we okay? Is my audio? My audio is okay, right? Because you were hearing Eddie Van Halen. Well, Van Halen, the band. I am. Oh, and my second goal was to get banned, to have this video to get a takedown notice.
Oh, it's probably dipped out of here.
Because look.
What? Hey, hot mic, Morgan.
Hi, Morgan.
Morgan, you got a hot mic. Thanks, man. Just, you know, we don't want to hear it. You know what I mean? Yeah, man. So what do I want to say about that? Well, in 305G, we're talking about things like YouTube blocking and the copyright law and fair use. It's a different, not our topic here today, but it is. I'm just pulling up the slides so we can keep talking about memory. But it is one of those paradoxes that if I actually play a minute, 30 seconds, in some cases 10 seconds, of some rando music from my past and try to introduce it to you guys as a new generation, then idiot groups are going to be like, no, wah, and no, take down, whatever. To me, it's absurd, but join us for 305G if you want. Literally, it's on YouTube, just like it's on Discord. Well, you have to get an invite to the Discord server, but it is on YouTube. And if you want to just go hit my channel tonight at 5:30. Okay, man, let's do this thing. Here we are. Oh, yeah. Let me see. I want to just, can I get a voice from, oh, actually, I know the audio is coming my way because we had Morgan on the hot mic. So I know we're okay.
You're welcome.
All right, man. Memory. Ready? And I'm going to I thought it worked really well last time for me to just kind of like stop me if you got a problem, question. The questions were great. And I'm just going to keep kind of pedal to the metal here and keep it moving. I think that was working pretty well last time. So I'm going to keep going. Yeah, I hope everyone, and I hope everyone's doing okay. Also, real quick schedule thing. Next week, second half of next week is fall break. No class on Thursday. Half a week off. That's all good. So class Tuesday, no class on Thursday. Okay. I'll talk to the TAs about, you know, what our schedule is going to be. I think we'll probably, I'm not sure what they've got going on. Zach can only speak for Zach, and only barely, you know, that, right, Zach? And we don't know what Talmadge and Vlad and, is that it? Who am I missing?
Are you talking about me?
Yeah, absolutely.
I heard my name.
Yeah.
We're only calling you names.
Of course.
Yeah. No, anyway, Talmadge, Vlad, Zach, we'll look and see what kind of schedule availability we can have still to answer questions. I mean, because I know that it's kind of a catch up time, and depending upon who's, what we've got going on, we might still be available. But we'll talk about it. Zach, Talmadge, Vlad, and we'll kind of just, what do we do, Zach? Maybe send out an announcement to everybody. Let's do that. We'll send out an announcement with just kind of general availability. I mean, that makes sense, right, everybody? To where you guys are trying to use that extra half a week to catch up, maybe. I know I will be. So, okay, cool. Jay's not wasting any time to launch in. So that's fantastic. And I just want to say that the Kinks version, here's the thing I just want to say while I'm pulling up these slides. You really got me by the Kinks, which is, what's the year on that? 1965 or something? The fact that Van Halen's version, other than the drums are more sophisticated, the guitar is obviously more sophisticated, that it actually resembles so much the original in many respects, is a tribute to the original. And they're both great, but they're just different. But I really like them both. Put another way, I can play the drums on the original. I don't think I can. I know I can't play Alex Van Halen's drums on the cover by Van Halen. Okay. There you have it. Okay, ready? Let's talk about memory.
You never answered my question.
Wait, what was your question, Zach?
Which do you prefer?
Oh,
David Lee
no, I
Roth or
think
Sammy
I.
Hagar?
Well,
think you
wait.
did.
Oh, I didn't hear the rest of that story. I mean, the rest of the question. David Lee Roth or Sammy Hagar? Dislike them both equally.
Okay.
How's that?
It's an answer.
I'll tell you after I finish the rest of this entire catalog. I have a love-hate relationship with both of them. And my sentimental favorite is David Lee Roth. David Lee Roth on the comeback, the resurrected Van Halen, not resurrected, but, David Lee Roth came back, right, to do some stuff. And he just, without the hair, and he just looks like your creepy uncle, I don't know. Actual pure vocal chops, different, but I got to go Sammy Hagar. All right. Here we go. Here's the deal. By the way, the meme. Oh, yeah, and yesterday I told you, right, that I was going to be on the television series, right? I did, yeah, I talked about it, yeah. So I can actually say it out loud. So the series is The Chosen. I can say it on the YouTube broadcast. This thing's going to get taken down anyway because of the copyright violation. But it's The Chosen, and this was from season 2, and I was there. I was on set yesterday, which was the first day of shooting, and I think that I will have potentially multiple opportunities, and with any luck, I might be. I'm not going to say like a regular character, but regularly appearing through season 2, which they're going to be shooting over the next 6 weeks.
You should show your picture.
Okay, I'm going to drop it. Yeah, what's the best way to show that picture, Zach? Should I just drop it?
Just drop it in the chat.
I'll drop it in the chat. Yeah. Okay.
All the YouTube people are gonna miss out. I'm sorry.
Yeah, sorry, YouTube people. Go to Discord if you want to see the chat on this one. Let me see. How do I do that?
So, who do you technically play in The Chosen? Because that's a really good show.
Yeah. No, I dig it. I'm a Pharisee, and you're like,
you Pharisee.
Right. And I know that for some of you, you're just like, that's actually kind of scary. How I think, does this work? There we go.
Oh my gosh, no way. That is like perfect.
I know, right?
You look just like a Pharisee, although I don't know what Pharisees look like back then.
I don't either, but I think I'm rocking it. I think I'm rocking the look. Anyway, and there was some adjustments to costume, but that was like preliminary costume thing. And anyway,
Are you a named Pharisee or just a one of
no,
yours?
no. Yeah, I am a named Pharisee. My name is Chuck, which was a classic first century Judean name.
Really?
And I spake unto Chuck. That even thou thine
Yeah, exactly.
iniquity, give all thou hast.
Anyway, but I think I'm rocking the look, right? I mean,
But
that's
Chuck hardened his heart and would not receive the words of the Lord.
no. You know, the really funny thing. We got to get on to topic here, but the really funny thing is, you can kind of see if you look kind of close, you can see the scar on my neck from my neck surgery, right?
Oh yeah.
You know?
Yeah.
But I had fusion, right, of 3 vertebrae in my neck. So, anybody want to run the punchline on this one? Stiff-necked Pharisee. Boom. I actually thought of a couple because you got that head thing on, right? And it's a little heavy. And then at some point my neck was getting sore, and I'm just like, man, I am a stiff-necked Pharisee. So anyway, yeah. So it was really cool. Zach's out of control, but so is Jay. It's fair. We'll let grudge match, battle royale.
Gosh.
Okay.
That Pharisee thing just like lit up a whole bunch of crap that went down with everything. But anyway, back to topic.
Not
Okay,
bad,
remember-
right? Not bad. I'll have
Yeah.
some better shots because there are shots. Anyway, last thing. There are
I honestly
shots.
thought that was a scratch. It didn't look like you had surgery, so.
Oh, okay. Yeah. No, but there's actually a scene, which I won't describe, but me and another guy next to me who's like slightly taller than me. So we're both like over 6'2". And the director actually came up to us and wanted us to do a certain thing, which I won't, they ask us like not to talk super details, right? But wanted us to do a certain thing, quietly, but like we're talking kind of thing. I'm pretty sure when season 2 rolls around, I will absolutely have some front and center, at least on episode 1.
So you will be visibly seen because I watch those shows, so I'll
Yeah.
have to be looking out for you.
Yeah, no, I'm a fan. I'm a fan as well, which is why I jumped all over trying to secure the opportunity to be part of that, right?
Cool.
I think it's great production, whether you've even got a religious bent or not. I think it's
either
really,
way, right?
really high
Yeah.
production quality from my view, unusually so. Anyway, we can talk more, but that's just sharing. Look, it's show and tell, share time. Okay,
Yeah, thanks for sharing.
yeah, I'll have better pictures once the series is out. Okay, so here's the deal. Memory. So we did, let me see, backing up here now. Remember this guy, the register? We did an individual RS latch, if you recall. I'm not going to back up because the animation's too complex, but there's the RS latch, right? And then we put this D latch around it so we could put data into it with the right enable. You may recall that was the thing. And then we strung a bunch of those together to make a register, okay? Well, it turns out if you can string like 8 of those together, that gives you a byte in memory. And then if you can, and you think about it, right? Look at this Q3 to Q0 to Q3. Remember the adder where there were like bits coming in? Well, what are those bits coming in? Q0, Q1, Q2, Q3. Those are the lines coming into an adder. And if I've got 2 of these, right, then then the Q0 from this memory and the Q0 from that memory both come in as like A and B into the first bit of the adder. Then the carry goes, and then the next one comes, and you just string in wires. But that's how you set this up. And then you can say, okay, adder, go, and it'll do its thing, which is kind of cool. So it turns out if you string like 8 of those, you get a byte. You string 16 of them, you get 2 bytes, right, or a word. And then if you can then string a bunch of those together one after another, then that's where memory, that's how you get memory. Like RAM, main, just regular main memory. And what you do basically is with that main memory, you just have them referenced using a decoder. So I can say, this is spot 0, this is spot 1, 2, 3, 4, all the way down to however much memory you've got, right? And what's the address of that first guy? 0, 0, 0, 0, 0, 0. What's the address of the next one? 0, 0, 0, 0, 0, 0, 1. 0, 0, 0, 1, 0. And you're just counting in binary, and you reference all of the memory locations. That's kind of cool, right? Okay, here's the tricky part. If I have an address that's only 1 byte, my address is 1 byte, right? 8 bits for an address. How many memory locations could I reference? Anybody want to take a gander on that? Well, and let me first of all, before you answer that one, what kind of notation, what kind of encoding or notation would you apply to that 1 byte of address? We talked about unsigned, signed magnitude, 2's complement. You know what I mean? What kind of representation would you imagine that 1 byte, as an address would it be?
I would imagine it as being unsigned because that gives you the most straightforward. It doesn't need to be negative.
Yeah. No, that's right, Michael. And I would even say, the intuition is straightforward, but the sort of specific aspect is that there's no concept of negative memory locations. You don't look at a street on a map, right? You don't go to Google Maps and see that, all the addresses.
You don't go to negative 273rd south.
Yeah, exactly. That's right. We kind of. Right. 273rd south is actually negative 273rd north.
Okay.
In Utah, where we use
Utah numbers
in the Cartesian coordinate system that we use, right? But essentially, every street in America, basically, I don't know that there's a street with a negative house number. It doesn't kind of make sense,
Unless
right?
it's underground, then that could be it.
If it's underground, yeah. I don't think so. I don't think so.
Well, they do.
I'm just kidding.
Basement floor is negative, but that's something else.
So, Cody, no one's hating on our street system, okay?
That's a weird niche.
I simply said it was a Cartesian coordinate system, which it is. Oh, you're just saying other people. I thought you were talking about this discussion. Okay. No, I totally get it.
Oh, others, yeah.
Yeah, okay, fair enough. Okay. So, it's unsigned. It starts at 0. So how many addresses can I have? It's like flashing you back to module 2, module 3, homework and exams, right? But how many addresses can I have if I had a single byte for my addresses?
Just 2 different values, right? Because it's 2 to the n.
Right? And what's 2 to the n?
2. With a single byte.
Wait. I think we're talking past each other. Yeah, I'm talking about a byte, not a bit. So I'm talking about 8. Yeah, it is 2 to the n. And I'm talking about 8 bits in my address. So I got a single byte that I'm using as the address to reference some spot. Keep going. There we go. Thank you, Jacob. 256 from 0 to 255. Because if it's unsigned and this is your, right, they're all on. 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. That's 255. But you go from 0 to that number. So that gives you 256. So the size of the address has to be big enough to reference the actual number of spots. And here's the trick. If you've been tracking with the decoder thing we've been talking about, you're going to realize as we get into it, we show you this little example, that the address is literally just like a little selector line into a decoder to turn a line on and leave all the others off. To just turn on that spot in memory. Literally. And so if I go if I've got 32 bits, right? Let's do this one real quick. 32 bits. I may have to do some math for you. I always do this one on the board, but if it's if you have 32-bit address, right, then the number of addresses you can have is 2 to the 32nd. And what is 2 to the 32nd? Well, 2 to the 10th, I think there's a slide. I think I made a slide. 2 to the 10th is approximately 1,000. Okay?
2 to the 32nd is huge.
1024.
That's right. 1,024. 2 to the 20th is approximately, Cody's probably right, but we'll come to it. 2 to the 20th is approximately 1 million. And then 2 to the 30th is approximately 1 billion. Because 1,000 times 1,000 times 1,000, right? 2 to the 10, 20, 30. That's kind of a cool little trick to just remember that when you're dealing with binary numbers, the tens go approximately 1,000, 1 million, 1 billion, etc. Which makes it easy to kind of go, well, 2 to the 30th is about 1 billion. And I said that there were 32 bits, so 2 to the second is 4. So it's about around 4 billion. That's at least the intuition. And then what did Cody say?
4,294,967,296.
Yep.
296. Yeah.
Exactly. That's right. So, I mean, Cody's right on, but it's really just, it's 2 to the 32nd. Okay.
Right.
Yeah. And shout out for that phone game 2048, or however you say it, 2048. I'm not even sure.
2048, 2048. It's not a big distinction.
Yeah. I don't know if there's like a vernacular, like you have to say it a certain way to be cool or whatever. Okay. So it's just, but that address is a decoder, which is kind of, it's literally used. It's not like that refers to that. No, it's the circuit's wired in so that when you have that address, it just turns on that location in memory. So that when I do the write enable, that's the one that gets turned on. Amazing. Anyway, and we're going to break it down. You're going to like this. Or not. But it'll be one of the two. Okay. So, we refer to the number as the address, okay? And the address is synonymous with the location. Now, this graphic, I'll tell you why I don't like this graphic. And you're like, yeah, but didn't you put this graphic in here? Why, yes. Yes, I did, because I'm a dork and I didn't make a better one. This one shows the memory with all zeros down on the bottom, and then the biggest address, which is all Fs, up at the top. Most of the time, I think that's kind of flipped, where the zeros start at the top, because that's like the first location. You know what I mean? But it doesn't matter which way it starts, as long as you understand the concept.
So you're wanting it to be, instead of being from bottom to top, from small to big, you wanted it to go from top to bottom.
My intuition and my emotion want that, but it's not wrong. It's not wrong either way.
Right. Yeah.
Okay. And I don't even know, I haven't done documentation to say that mine is the most prevalent or the least, or I don't even know. It could be that this
for you wanted the best representation, right?
Yeah, for me. And this one isn't it. Just want you to know that for me, a lot of times when I start drawing pictures, I will pretty much always start with 0 at the top and go down. That also I'm never going to live down the Pharisee thing, right?
Contradicting
thanks, Cody. Anyway, yeah, but that's the idea of memory, okay? Now, in this case, we've got a value in memory, okay, of 8 bits. And how many memory locations do I have? But you can see that there's this many, 1 plus whatever that number is. And that's going to be 8,
Holy crap.
16, no, that's 32. That's 32 bits. Yeah, that's actually the example of 32 bits. Okay. All right, let's keep going. So there are a handful of terms. One is that we call the address space. Now, by the way, one of the things that I really try hard to do on the homework and the exams is to not, ooh, wow, didn't mean to jump over there yet. There we go. Is to not turn this into like alphabetical soup and rote memorization, kinds of stuff. And so when you come to certain terms like address space, that just refers to the amount of addressable memory. So that just says like how many bytes are in memory, okay? Now, in this example over here, every spot in memory is 1 byte, but it doesn't have to be. In fact, it's almost never 1 byte. It's not uncommon. That could be 16 bits, right? 2 bytes. It's almost always a number of bytes that's a power of 2. So it's like 2 byte, 1 byte, 2 bytes, 4 bytes, 8 bytes. That's the common, again, because this binary thing makes circuitry easier whenever you're dealing in powers of 2, right? So, so in this case, if I say that there's 16 meg of memory, I'm talking about 16 megabytes of memory, and which is a ballpark 16 million, right? Or in other words, 16,777,216 to be exact. And then this is the burning question that is the kind of thing you do need to understand, which is how many bits would you need to address that many bytes of memory? Okay? How many bits would you need for the address, right? Back in this example, we had 32 bits, so there was about 4 billion addresses. Here, yeah, go ahead. Did I have a...
Yeah, you have 24 bits, right? Because 2 to the 24th power.
Yeah, no, exactly. I mean, and Big Mondo hint is right down here, right? But essentially, that's right. I would need 24 bits because that's how many addresses I have to be able to reference. From 0, the range would be from 0 to, on the low end, to 2 to the 24th minus 1 would be the biggest number at the top, right? And 0 at the bottom, which would give me 2 to the 24th actual addresses. Okay? Now, this one's a little more advanced. I'll throw it out just to noodle on, and then I'll answer it quickly. There's an assumption. The question is, what's the assumption built into this question? And, well, maybe there's not an assumption, but there's an assumption you have to kind of deal with, which is how many bytes are at each location. If I told you there were 16 meg of memory, right, you would know that there were 2 to the 24th bytes, but you don't know how many bytes are at each location. You see what I mean? I mean, it could be 16 bits in every memory location. It could be 32 bits in every memory location. So there's 16 million bytes, but if it was 2 bytes in every location, you'd only have like 8 mega addresses, right? And if there were 4 bytes at every location, and I've got 16 meg of bytes total memory, well, every memory location is 4 bytes. So I would have 4 million, addresses with 4 bytes at each location, hence 16 million bytes. Does that make sense? And this will throw a few people off, always does. But this is the fundamental idea that I can have a total amount of memory, but the total amount of memory is the number of addresses times however many bytes we have in a given address. And that all has to be the same. But like if I've got 4 bytes per address and I've got 1 million addresses, I've got 4 million bytes or 4 megabytes. Okay? I'm going. This is the little interlude that I was kind of talking about a K byte is 2 to the 10th, literally 1024, approximately 1000, right? A meg, around 1 million, 2 to the 20th. A gig, about 1 billion. A terabyte, about 1 trillion bytes. These are crazy. These are actually crazy numbers. But this is one, since for some of you, you're still new in this kind of, technical field. You know what I mean? Some of you are like longtime, computer geeks. And some of you are kind of just new to the whole, like, I think I might, be interested. And you don't have this fluency. So this just kind of helps you when they talk about how many K, how many meg, how many gigs, how many terabytes. And one of the other really, really weird things, I'm going to draw this for you. We refer to and I don't know why this is, yeah.
So with that address space slide, I just to understand it real quick.
Yeah.
Where it says like 1 terabyte of equals roughly what?
A trillion.
Is that trillion bytes. Yeah. Trillion bytes. What was the 1,000 gigabyte? Okay, never mind. That's just okay.
Yeah. No, all good, man. Because each one goes up by 2 to the 10th.
Yeah, I was just thinking about, like, you were saying. What was it about? It's not 1 trillion addresses. Is it 1 trillion bytes of addresses? What was it? No, it's just one.
It's just bytes in memory.
Okay.
And until you know how many bytes are at each location, you don't know how many actual addresses there are.
Okay.
Because if it's 1, then the answer is just whatever that is. If it's 2, then it's half of that.
Gotcha. That's just the actual bytes.
Yes. And then this is how we say it. Again, I don't even know why this is the case. It's Ks. We don't say kilos. Kilobytes is what that literally, right? We say how many Ks or how many K? How many Ks? I think we mostly say Ks. Then we're like, how many megs? How many meg? How many megs? I think, oh my gosh, I pluralized with an apostrophe. I want to repent of that real quick and get rid of that. How many megs? How many?
To the English police, they will be coming for you.
I know. I myself am a member of the English police. That's the problem. How many megs?
Sir.
How many Ks? How many megs? How many gigs? And then we don't say how many teras. So that's the letter. We don't say Ks, Ms, Gs, and Ts. And we don't say like kilos, megs, gigs, and teras. And we don't say kilobytes, megabytes, gigabytes, and terabytes. It's inconsistent, but that is the thing. Ks, megs, gigs, and terabytes.
So something that I've noticed, Dr. K, is that for each byte, like for 1 gigabyte, it's 1,000, and then it increases by 3 zeros on the right-hand side of the rough estimation. So 1,000 bytes for a gigabyte, 1 million.
Wait, for a kilobyte or a K byte.
Kilobyte, yeah, sorry. Kilobyte. And then it increases by 3 more zeros after that, and it constantly increases by 3 zeros. Is there any relevance for that, or am I just completely stating something that's really dumb?
Well, no, it's not dumb. It's not dumb, but it's sort of, if you look at it this way, right? 2 to the 10th is 1,024, or around 1,000.
By 10, yeah.
Because 2 to the 20th is 2 to the 10 times 2 to the 10.
Right, yeah.
AKA 1,000 times 1,000, which is 1 million.
Right, yeah.
Times another 2 to the 10th, which is another 1,000, you're at 1 billion. So it's just like that's the pattern. Inherently. The cool part is simply that 2 to the 10 is around 1,000. You know what I mean? Once you get the idea that 2 to the 10th is around 1,000, which is just funky and cool, I don't know, right? You know what I mean? That kind of like lines up with decimal is coincidental, I think, and cool. And makes the rest of the approximation and estimation a lot easier.
Indeed.
All right. Let's see. Now, okay, so this is kind of expanding on this idea. We talk about addressability. So we talked about the memory space is just like how many bytes, how much raw material. The addressability is I'm going to do an example here for you, but addressability has to do with how many bits or how many bytes are at each location. We'll get to those terms a little bit better. But I'm going to actually we're going to do the amazing memory that has 4 bytes in this memory, and every byte has 3 bits. Okay? Every memory location in this dumb little example is going to be just 3 bits, okay? Now, I have to warn you, you're going to feel a little disoriented right now. This is normal. You will soon gain your equilibrium, and then, anyone else besides me watch Tenet yet?
I've seen that. So trippy.
It's very trippy. And I have to say, when I watched the trailer and told my wife about it, I was like, yeah, I saw the trailer. I still don't have any idea what the movie's about. I don't have any idea what it's about, but I think we should go see it. So that's anyway.
That's Christopher Nolan movies.
That's Christopher Nolan, right? And in fact,
so little.
Before I realized that it was a Christopher Nolan movie, and before I fully realized that Inception was a Christopher Nolan movie, I actually said it reminded me a lot of Inception.
Yeah,
So-
I didn't know until after having watched it that it was this. I knew going into it was Christopher Nolan, but I didn't know that meant. I didn't know
Yeah.
he was the guy who did Inception.
Yeah.
After
And
finding
so
that
no-
out, it
and
made
it's
a lot
not-
more sense.
That's right. It's not the same plot, or saying that it's like Inception, only in the sense that it's trippy.
Yeah, yeah,
And it's one of those
exactly.
things. Yeah, it's one of those things too, where A, please no spoilers for the others. B, I don't even know how to tell you the spoiler if I wanted to. So I have to watch it 3 more times. And you're like, why am I talking about this? I'll tell you why. Because that's why. Because the first time you see this, it's kind of like a Christopher Nolan movie, and you have to just okay, look, don't worry right now. Let it kind of wash over you. You got to go through this a few times, and just like the other circuits that we've done, the first time you see it, it blows your head a little bit, and then you just have to okay, just pause and break it down. Okay, now, and the reason that this thing is 4 bytes is because the number of memory locations, kind of needs to be a power of 2, and 4 will actually tell you the tale. And the number of bits is kind of arbitrary. That's just just stretch the picture out. So you don't add anything by adding more bits out to the right. And we're real estate limited, and you still have to show what's going on. Okay. So it's the smallest example you could probably give. That's where we're going. As you know, I've got my big screen here. So when when I'm looking over here, that's me, and that's me looking at my big screen, which looking at my small screen from the monitor, from the streaming stuff, it's too small for me to actually see it
So
through the
Dave,
monitor.
this is this is just for example's sake, right? This one
Yep.
byte highlighted. Okay, in red. Gotcha.
That's right. And outside of Minecraft, probably somebody maybe did this. This is like a memory that has never existed in the real world. You know what I mean? It's pretty worthless. Although, tiny little registers are just a single 8-bit, thing or whatever. So there's probably stuff like this that has existed in memory for tiny little purposes, but it's not, but this is the idea behind a general purpose addressable memory. And addressable just means you give me the number and I can go to that spot in memory and go get its value out for you. That's what it means when you say addressable. That there's addresses from 0 to 2 to the n, where n is the number of bits in the address. Okay? And a lot of this will make the LC3 make sense when we get to that part and we start doing programming stuff. Okay. Where shall we start? So this right here, as you can see from the label, that's a byte in our little tiny memory. That is address 0. That's address 01, 10, and 11. Everybody cool with that? Just to show you, what the pieces are. That A right there is the address. Okay? This is the data lines coming in. And then these are kind of like the data lines going out. And notice that this guy down here, this pink vertical bar is a decoder. And the values that go into that decoder are the address. So notice, we can actually look at it. When that value, and by the way, A, 1, and 0 just refers to the fact that there are 2 bits. Okay? I don't think that's built as an example. No, that's right. It's not an example. It just shows you that you've got, 0, bits 0 and 1. But when you look at that address, when it's all zeros, 0, 0, can you see right there that this decoder is set up so that would turn this line on. If it was 0, 1, it would turn this line on. If it was 1, 0, it turns that line on. And if it's 1, 1, it turns that line on. So can you already kind of see, even without knowing how it's actually working, do you see how I'm like, okay, when the address is 0, 0, that line turns on and the others are off. That's how a decoder works. And when the address is 1, 0, then that line turns on and all the others are off. So that's how the address goes into the decoder and just turns on one of the spots in memory. Okay? Now the details of how we do that, we'll show you. Okay? But that's how that works. That's the data that's coming into memory. So this thing is going top down. Okay? Data comes in the top and goes out the bottom. And then this is used when you're reading data from memory. Okay, so this is the key. When I'm reading data from memory, I don't care about these datas up here. When I'm putting data into memory, I don't care about these down here. Okay, I care about only the one I'm caring about. What else? Okay, now here's what we're going to do. We're going to seed this with random. This is truly random, the ones and zeros and stuff here, right? That guy's all zeros, that guy's all 1, etc. These are just, and you're like, well, how does that 0 get in there? Remember the D latch and the RS latch, the gated D latch? This is a gated D latch with an RS latch inside this little bucket. And what that 0 actually means, if you can see it, and I apologize, the pink was actually part of the publisher's graphic, and I didn't want to make my own because I'm lazy butt, and but that pink is kind of just built in. I probably would have made a different aesthetic decision myself. But what I'm trying to show you right now is, remember how on the RS latch and then with the D latch there was a stable value up. We had A at the top and B was at the bottom. There's a stable value. And that's what's representing it's representing the value of that particular bit. So if that A was 0, then the value in that gate is 0. If that A was 1, then the value is 1. So what you can see here, notice the little line right there. And then over here where there's a 1, that it's kind of got the little thicker red. Can you see it?
It can be seen. I don't understand it, but I can see the red line.
It can be seen. Yes, that's accurate. I'm hoping that's what you're seeing. But yeah,
you're saying the one in the middle, the red line that's going over, is less thicker than the one on the very right-hand side?
No, I'm saying that wherever you see this little red line, it's because there's a 1 in the pit.
Oh yeah. I see the red line.
Yeah, that's all I'm trying to show there is that that guy has a little 1, and wherever it's a 0, it's just the plain black. Make sense? It's kind of a representational weakness that's a lot easier when when I'm in class and we're on the big screen and I can walk over to it and, stand there, which is what I normally do when we're not in the middle of a pandemic. Okay. So, all right, yep. So what we want to try to do is read the value of the 3-bit byte at memory location 10. Now, you know what? That is going to be our value. Those are the values. But we're going to read the 3-bit byte at memory location 10. So this is 00, 01, and 10. So it's this location here. Okay? We would view it as the third. Okay. And we're reading, so we don't care about the top. We only care about the bottom. And what we're going to do is we're going to walk through this. Now, what I recommend you do, kind of like watching a Christopher Nolan movie, is come back to this and rewatch the video on YouTube. The slides are on Canvas. You can also grab the slides and just step through it yourself at your own pace. Or you can rewatch it, okay? Alrighty. So here's what we do.
Go through each one. Is that what you're going to do?
What's that?
Are you going to go through each one to show it?
I'm going to go through a couple examples, but
Okay.
not every one, because the principle will be the same. So, okay. So there's A where the value is 10, right? Because that's the memory location that we're selecting.
Right.
And what you notice is, right, the 1 goes into this gate and it blows up, right? Nothing comes out. Goes here, blows up, nothing comes out. But the 0 into the NOT and the 1 straight into the AND gate means that you can already tell that that guy's going to survive and this guy's going to blow up because you got a 0 coming in to an AND gate. Okay? So that's what you see here with the thick red again. When that address is on, this is what is on. You can kind of see them going, right? They're out here, goes into here, here, and here. Now, if you look at it for a second, what you can kind of tell is, you're like, okay, but what stops? If you look at these out here at the end of every bit, there's an AND gate, all right? And then all those AND gates, if you look top to bottom, they sort of cascade down, and they go into the same OR gate. This is my impersonation of an OR gate. And they go into the same OR gate, right? And you're like, well, why doesn't everything just dump out? Well, and the reason is because every one of these guys is protected by an AND gate on the back end. And one of the values coming into that AND gate is the value of the bit. And the other one is the value of this address line. So, because I've got a decoder here, when I turn this line on, boom, that gate is on. On, on. And every one of these other gates are off. So only, value 2, address 2, address 10, if we want to call it that. That's the only address that's going to actually fall through when we're ready to have it fall through. Do you see that? Isn't that kind of cool? And that's just the address decoder that just turns on that location in memory. And if the thought has already crossed your mind, yeah, but what if I've got 64 gig of RAM? Are you telling me? And the answer is yes, I'm telling you. All these wires, 64 billion of this, and one of them turns on, and all the others are off. Insanity, but true. Okay. All right, so that decoder turns on that line and only that line. Now, I'm trying to read right down here, right? So what do I have to do next? It's just going to ripple. That guy's now turned that on, so that value is now going to drop into the OR gate. Same here, same here. Now, this happened to all be 1s in this example, but it didn't have to be, right? If it had been a 0, then that line would be off, and the values coming out to D would be 110. right? And then it just pumps out, just drops out the other side, and there's our values. That's it. Literally, it's just like throw the line for that one, and then those values drop out into D0, D1, D2. Now, we're going to talk about later on in the LC3 architecture, we have a thing called a memory address register. It's a little chunk of memory that holds the address we're looking for. In this picture, that's A. And we have another thing called a memory data register, which is the data that either is used to put the data, to put something into memory or to catch it when it comes out of memory. That's D. Okay? Right, yeah, so thank you, Mr. Jones. If you're talking about what I'm saying and not the latest GIF. Okay, that's it. That's reading. Now, there's one other question that I know some of you are asking, which is like, okay, then where does this go? And the answer is that it goes into another bit of memory, a register, which is a bunch of D latches. It moves it to a separate bit of memory, and the CPU has control over, when it wants that to go somewhere else, and all of this control, like when does that line turn on? When the CPU says to turn it on. The CPU is just like, turn the crank. It knows what to do. The circuitry of the CPU is built so that on every clock tick, it does whatever the next thing is that it's supposed to do. That's how it goes. Anyway, and then you turn that line back off. All right? That's it. That's how you read from memory. We're going to keep moving at high speed, and we're going to do, we're now going to write a value into memory. And what we're going to do is we're going to write the value 001 into the 3-bit memory at the same location. Okay? I mean, imagine that you pulled a value out of memory, and then you just like fiddled with it, and then it turned into a different value, and then you like put it back. That's kind of what we're doing. All right. So here we go. So first of all, the value we're putting in is 001, and we're going to just put those up here at the top. There's 0, there's 0, there's 1. And so that line is on. This one's on, and it goes all the way down. It literally touches all 4 rows, right? You're like, wait, why are you touching all 4 rows? I mean, isn't that going to screw a bunch of stuff up? And the answer is no, because we are going to, play with that line. That selector is still going to be there helping us. This guy's just 0, so that's boring. Nothing, it doesn't look any different, right? And the other thing that we talked about, remember, like this data is coming from somewhere, and what you realize is it's really just, remember the data line coming into the D latch? It's just that data coming in, to these 1-bit memories, but there's multiple of them, right? So there's the 0th bit, the first bit, second bit, etc. Okay, now we're ready. So the next thing that happens is we throw the address line. We let the address, notice, boom, animation. That address is going to turn that guy on, and there you can see it, right? So this guy now becomes activated. So I've done really 2 things. From the left side, I've turned on the right, the correct location in memory using the address as a selector into the decoder. The address tells me which one to turn on. Oh, this one? Yes. All the others off. Got it. Then the data is simply rippling across all the memory. Like I'm literally like this guy here, this D sub 0, that guy, he's literally set up to go, I'm going to fiddle with the 0th bit. I'm going to be poised to touch the 0th bit of every single byte in memory, every single location in memory, which is kind of crazy. And then you're like, yeah, but it feels creepy. Like you can't be touching everything. Well, this line right here is going to help you. Okay. Where are we at? Unfortunately, I got to draw this a little bit better, but anyway, we'll get to it. We'll get to it. Because while this stuff, here's the thing to keep in mind. This value of 1 is set up and it goes here and it goes here. See it? And then this value of 0 comes down and it goes there and it goes there. That's exactly what we did with that D line. If you remember, the D line went to the R and the S, right? It went to the top and the bottom, but nothing happened until, anybody remember? Recognize our friend, Mr. Right Enable? Until the right enable goes pop, they go do the thing where you throw the power. Nothing can make its way into these gated D latches, okay? So when we hit the right enable, boom, we hit the right enable, and again, the address already turned everybody off except this one. But this now, the right enable can come through because the address turned it on, which means that the rest of that goes on. And I've now got a right enable touching this guy with the zeros coming, that another one with zeros, and this guy with the 1. And when that happens, and we could break this thing all down, but this is just what we did in the RS latch and the D latch. So to get this kind of really fluent, you got to go back to the RS latch, watch those videos again. Look at the D latch, watch that, grab the slides, walk through it. That's what's happening underneath here. Okay? And you're like, in the meantime, like, what's happening over here on this data line out the bottom? And the answer is, don't care. It doesn't. We don't care, because that's just sitting there changing, because it might be, it's actually connected to the MDR, but the circuitry is not turning it on, so it's not going to change anything in the MDR, the memory data register. Okay, I turn the right enable back on. I turn it off, and then I'm just back where I was, and I just put that value into the memory. This is why you have to watch Christopher Nolan movie a bunch of times. And I think, yeah, that's it. Any questions? I might be Chuck Nolan, who was once a Pharisee and then became a filmmaker. Okay, now this is your chance, and I'm okay, coming back and toying around. I'm also okay just kind of moving on and saying, look, it is there for the record, and you've got access to it, and hit it again. We can also do, if we want to, one of the things that helps is sometimes when, this to me is one of the more trippy ideas, because we take, we were just talking about decoders and multiplexers and adders and, and all of a sudden we're taking ideas from those and then straight up decoder, right out of the decoders. And we're building, memory. We take the RS latch, the D latch, and a decoder, and then the principle of stringing these together, which we learned from adders, and when you're done, you've got memory. And I can actually I can write stuff in, I can pull stuff out. Amazing. Pretty cool. I'm just going to roll, unless there's somebody stopping me. But we can do another, if we need to sometime, we can do like a help section. I've done that sometimes. If there's like some demand on any of the subjects where you're like, I've watched the video a bunch of times, but there's maybe like 20 people in the class that now that you've watched it and it's a lot more fluent, it's like now you want to, like roll back and ask a bunch of questions, because you're more, you know what I mean? You can't even ask the right questions. until you've been to a certain level of understanding. Okay. All right. Now we're actually almost done with this. We got 15 minutes. We're going to get close to the end of, what is this, module 4? We'll get close to the end of it. But I don't think we're going to get quite all the way through it. But we might. We might. In which case, we're going to set the due date for module 4, for a week away. And then start slapping a bunch of zeros on it, which, by the way, was motivational, it turns out. So we're happy to oblige. Okay. Now, we talked about combinational logic circuits, which is a fancy pants way of just saying, okay, if these are the lines, then this, if this is what's coming in, then that's what's coming out. But there was no sense of memory, right? There's no sense of hanging on to, some stable thing. If the line ever changes, then the circuit just pumps on through. It's like I don't know, like a water hose, it's like a valve in a water hose system or something. That's probably a horrible example. And then we talked about memory circuits, which could store information, but it didn't process it. All you could do with that is put memory in and, read it back out. A sequential logic circuit does both of these. And it turns out there are certain kinds of things that you can do if you've got both of these going down. Okay? So, and this is our interlude to talk about combination versus sequence, and to kind of introduce you to states and state machines, okay? It's the very sort of preliminary. You're going to get a lot more into state machines, finite state automata, and things like that later in the curriculum, in the program. But we're trying to kind of just introduce that idea here. It's a very powerful and very important idea.
Can you go to the last slide just one more time, please?
The previous? That one there?
Yeah.
Yeah.
Yeah, real quick. I need to just write something down. Thank you.
Yeah. Am I good to move on?
Yeah.
Okay, all right, thanks, Tyson. Okay, so here we go. So look at these two. These are both combination locks, right? These are both padlocks. What's the difference? What say you?
Time is the difference.
Explain.
Well, so you've, on this lock to the left, you've got the 0th, the 1st, the 2nd, and the 3rd places, right?
Mm-hmm.
If I set the 0th number to its correct digit, and then I do the 2nd, and then I do the 1st, and then I do the 3rd, it will still unlock for me, just as if I had done them from left to right.
Yep.
But if I know the combination for the lock on the right, but I do the 0th number, and then the 3rd, and then the 1st, it won't unlock for me.
That's right.
Because the key distinction is not which numbers go together, but the order in which you enter those numbers.
That's right. Correct. Exactly. And when you said time, that's probably not, it's probably not quite the right term, but order absolutely is, right? It's like order and sequence. Like I've got to do this first, then I've got to do this, and then I have to do that. That's the sequential lock, the classic,
I was thinking sequential as well, yeah.
Yeah, and whereas the other one is just purely the combination. Like the order doesn't matter. Once they all line up, it opens, right? So that's absolutely right. The key here is that for that combination lock on the left, there's no state information. That's really the key. Is if you think about things that have order, they have states, okay? And we're talking about like a state of being, a state. Like, what's some other examples of it? Well, that's the technical term. We call them states. So I'm in like when you wake up in the morning, you're in the asleep state. Then you're in the swearing at the alarm state. And then you're at the, like out of bed state. And then you're at the, the sugar puffs, Cocoa Puffs state. You know what I mean? There's these discrete kind of states you pass through, and I mean that's really a bad example, but it turns out that there is a lot about our lives and about just whatever the world. You're in the nighttime state. Now you're in the twilight state, or you're in the what do we call that in the morning?
The coronavirus state?
No, yeah, we're in the coronavirus state. No, when it's night, what do you call that in the morning when the sun comes up? It's not
inside.
dawn. I'm such an idiot. Yeah, that's dawn, and it's dusk on the other side. So you're in the clearly nighttime state. Then you're in the dawn state. Now you're in the daytime state. Now you're in the dusk state. You know what I mean? And the planet just rolls through these 4 states. And if you ever either skipped a state or kind of went backwards or out of order, it would kind of screw everything up. It would be weird, right? The world would be functioning differently than what we would expect. I don't know if that was a great example or not, but I know I never give the same example twice when teaching this, but okay. But, so this is one. The state just means that the order in which you do things, you have to be in you have to put the first number in. Now you're in that first number state. Okay? From that state, I can now do the second number. But if I did the same second number when I was in a different state, it would not work. It would screw it up. So I've got to be, in this particular thing. What would be another example? I think maybe to go to law school, you have to have an undergrad degree. So you have to be in the undergrad state, then in the graduated state, then you're in the law school state, then you're in the graduated state, then you can pass you're in a state of being eligible to take the bar exam. Then if you pass that, you're in the attorney state, and if you fail it, you're kind of back where you were in the I've got my degree, but I don't have my license to practice law or whatever. I'm just trying to think of things that have a certain sequence. Yeah.
So basically one can't function without the other, just like the combination lock. If you have a different input the second time and it's false, then the combination will work, right?
Yeah, that's right.
Just like one thing to another, law school, you need other prerequisites to get to that specific school. And without those prerequisites, you wouldn't be able to make it to that state of law school.
That's right. That's right. And the same thing with it's all around us, right? Like some of you, there's certain courses you can't take until you're matriculated.
Yeah, that's a good example.
So you have to be I want to take that class, but I have to do these other things. That puts me into the matriculated state. And then now that I'm in the matriculated states, I can now take those classes, but I couldn't until I was, etc. Life is full of that, is the bottom line. And so it turns out that software, which both interacts with life and, has to, resonate and coordinate and model life, also is going to, reflect those states. So therefore, representing states in software, very important. Because software models the world or interacts with it or both. Okay, so we're going to introduce you for the next 5 or 10 minutes. I'll probably go, I don't know. I'll see what I can get through. But here's what I think I'm going to do. I'm going to give you enough of this to set the deadline starting today. Yep, that's just what a nasty Pharisee I am.
So until next Thursday is what you're saying? Like you said a week?
Yeah, we'll set this. Because we'll do 5 more minutes. And it'll give you enough. What's that?
Curse you, Chuck, you stiff-necked Pharisee.
Exactly. I am. Okay. So these are the things that we call this a finite state machine. Finite because it's not infinite, and there are states, and it's like a machine. You turn the crank, and something happens, and you can move from one state to the other, which I'll give you some examples. You got to have the states. You got to have ways to get in, ways to get out, specs for what the transition is and things you do when you're in that state. Okay? Here, this is an example. Traffic light is a good example. The traffic light has 3 states. Now, we are assuming a world in which the transition between green light to red light, where each transition from light color, so green to red, red to yellow, yellow to green, which is different in parts of Europe, right? Where it goes green, yellow, red, yellow, green, yellow, red, yellow, green, and it moves up and down, which I prefer. You know what I mean? Because it gives you a heads up that the light's going to change. Because in Utah, I swear about 20% of the drivers, between when it goes to red and when it turns to yellow, solid nap time, man. They go into harsh nap zone.
Easily.
Which is okay, unless you have, we can do a statistical analysis of this, but depending upon the number of lanes, okay, the odds go down as the number of lanes go down. Sorry, the odds go down as the number of lanes get bigger, because if it's like a 4-lane boulevard, for everybody to stop, all 4 drivers at the front have to fall sound asleep. So, and you got about a 10% chance of that happening no matter what. So you've got 0.1 times 0.25 times 0.25 times 0.25 times 0.25. Is that right?
We'll say it is.
Yeah. No, I think that's actually right. And that's the chances that on a 4-lane boulevard, everybody falls asleep. And then someone like me has to go kindly. I'm not like, wah, you know what I mean? That's more East Coast. And wake them up, gently nudge them. They're just doing they're doing this. But if there's only 3, if there's only 2 lanes, you only need both drivers to fall sound asleep. And if there's only 1 lane, you only need the 1 driver to fall asleep. So fewer the lanes, the greater the probability. The yellow light throws an interrupt at them that has a greater chance of alerting them when this next interrupt hits. It's like people just forgot they were in their car. Like they just forgot that they were just sitting at an intersection. I don't know how that works. Anyway.
Well, that's definitely relevant nowadays because of the coronavirus.
How so?
Well, a lot of people are forgetting the state in which they are in sometimes. Because they're so bombarded with coronavirus stuff, yeah.
That could be. Okay. But there are 3 states. The transition between these states, we're going to just say, is instantaneous. But it's truly not at a atomic level or whatever. But this is discretization, right? From an analog perspective, where's the you know what it looks like when the red light's on. You know what it looks like when the yellow light's on. What is the precise point down in the circuitry at which you would say, I'm now in the red light is on versus I'm now in the yellow light is on? That's actually a very difficult question when you get right down to it, even when it's a computer system. Okay? But we're just going to go, we move from green to red, green to yellow, and that transition is instantaneous. That is not truly, not really true, but it's our discrete approximation of reality. There's behavior in every state, right? So when I'm in the green light state, the behavior I do is to
go forth.
Turn the light on. Just turn that light on, and the other lights are off. But when I move into the green light state, I turn the green light on. When I move into the yellow state, I turn off the green light and I turn on the yellow light. Right? What's the transition? What causes the transition? What's the action, do you think? Simplest example. Let's go with simplest example. What say you? Take a chance.
Can you repeat the question, please?
Yeah, what's the simplest example you can think of why the trigger to transition you from a green light to a yellow light?
Electricity?
No, that's the power by which it happens. What's the event that suggests that now's the time to change that light? Huh?
Would it be just like a certain amount of time passed, or?
that'd be the easiest, right? Just like this stable rotation. Clock goes, right? Motion detectors, another one. Like weight detectors. I don't even know exactly what those systems are, right? But like a car pulls up, it checks whatever, and it goes, yeah, we can transition you. But there's some event that happens that triggers the change, okay? And so there's some kind of trigger that's gonna cause it to transition. So this is the dumbest example, right? I'm in the red state, red timer expires, I transition to the green state, green timer expires, transition to yellow state, yellow timer expires, and I just cycle. That's it. That is a finite state machine. So when I say, draw a state machine, and the homework has you like coming up with your own example of a state machine, just look around you. It has to be simple enough that you can articulate it. That's it. That's all it's asking for. Okay. Now we're out of time, and I'm going to come back to, okay. Let's pause right here, and so Zach, let's set the deadline a week from today, because really you have what you need to do that exercise. The rest is just reinforcing it a little bit. Okay? And you can do, and the other stuff is going to kick your butt anyway. The other circuit stuff is going to be a lot. This is not the hard part of the homework or the exam. All right, cool. So I'm going to...
Thank you.
You bet. I'm going to take us out with a little more... what do I need to do here? We just need... Here we go.